Well, welcome back to our video instruction series. With our next reading, we're going to cover statistical concepts and market returns as we continue through our study session of quantitative methods, our first study session of quantitative methods, basic concepts. So let's take a look at what we need to cover here. We're going to learn some terms. First off, some statistical returns. Descriptive statistics describes the properties of a large data set. So, descriptive statistics. What's the average? How spread out they are, how much variation there is in them. These are the descriptive statistics we'll have. Now, inferential statistics is when we take a sample from a population. So we've got some annual returns on an index fund, and we want to make some probabilistic statements about the characteristics of the overall population. So using a sample to estimate some of these descriptive statistics. When we talk about a population, we mean the set of all possible outcomes of a random variable. And a sample is a subset of the outcomes. Now, if you think about stock returns, say the returns on the U.S. market, some index of U.S. markets, we may have 80, 90 years of data, but that's definitely a sample. Because remember, it says for a population, all possible outcomes. Well, we're never going to see all possible outcomes. We're always going to see a sample. So as we go through this, remember, most often we're dealing with a sample. Having a population would be an unusual situation, especially when we're talking about returns on a stock, returns on a stock index, bond index, anything like this. Now here we have our 4 measurement scales. We've got a learning outcome statement. Notice that the command word here in the upper left-hand corner is distinguish, so we need to distinguish, that is, tell the difference between these 4. Now we put NOIR up there, that's noir, it's the French word for black, which has nothing to do with what we're doing except for those are the letters of our 4 measurement scales, nominal, ordinal, interval, and ratio scales. So let's see if we can, in fact, distinguish among these. Now, a nominal scale, if you think nominal, I just want you to think name, because only the names make sense. So if we had some birds and we were going to put them in different categories by their species, I think it's a species, type of bird anyway, robin, parrot, and hawk, we could do that, but those are only names. There's no relation among the 3 groups. We can't really put them in order or talk about measurable differences between them. So that's our next measurement scale here as we go through these is ordinal, and here the order is what matters. So if we divided stocks into 3 categories, large capitalization stocks, mid capitalization stocks, or small capitalization stocks, now the order makes sense. We know large is bigger than mid, and we know mid is bigger than small. Okay? We don't know much more than that. We don't know any quantitative measures here, but the order makes sense. So that's an ordinal scale. Now, the next scale is the interval scale. The intervals make sense. So rather than using financial terms, think about temperature. We can say 40 degrees is 10 degrees greater than 30, or 30 is 10 degrees greater than 20. But what doesn't make sense here is a ratio. If it goes from 1 degree Fahrenheit to 2 degrees Fahrenheit, hardly anybody would walk outside and go, it's twice as warm as it was yesterday. As a matter of fact, hardly noticeable. So with an interval scale, the ratios don't make sense. 40 degrees is not twice as hot as 20 degrees. And so that's our last scale, the ratio scale, where ratios make sense. And ratios make sense if there's an absolute 0. And absolute 0, well, we have that concept with temperature on the Kelvin scale, but what we have in money is when you got $0, you got no money. So that's your absolute 0. So we can say $200 is $100 more than $100. That's the interval scale requirement. But we can also say $200 is twice as much money as 100. 100 is twice as much as 50. And this works when there's an absolute zero. So it certainly works when we're talking about money values. Some more terms for us here. A parameter describes the characteristic of a population. So the mean, the average, is a parameter that would describe a population. Where is it centered? We will also talk about the standard deviation, or variance is a parameter of a distribution or a characteristic of a population. And that is, okay, here's the mean. How spread out is it around the mean? We'll introduce the terms of skew. That is it symmetric, or are more of the observations over here, further out? Are there difference between the two sides of the mean in terms of the distribution? So those are the parameters we'll be talking about. A sample statistic describes the characteristic of a sample. So the sample mean is a sample statistic. If we have some ping pong balls with numbers on them in a big barrel, and we draw out 10 of those, add them all up and divide by 10, that's the sample mean. And we'll use that as an indication, sometimes as an estimate, of the mean of the underlying population. A frequency distribution is just a table that summarizes a large data set by assigning the observations to intervals. So let's take a look at that. A relative frequency distribution is going to show the percentage in each interval. When we talk about a cumulative frequency distribution, it shows the percentage of observations less than the upper bound. So if there's 3% in this first interval when we do a relative frequency distribution, and 5% in the next highest interval, well, at that next highest interval, we'd say the cumulative frequency distribution is the sum of those. I think I said 5 and 3, so that would be 8%. And that just goes on up to 100%. When we get to the absolute highest value of the distribution, then we've got 100% less than that. That is to the left of that if we're thinking about looking at a number line. So here's a histogram. The histogram just shows frequencies. So on our left-hand axis over here, let me find my magic pen, okay, we've just got one observation in this first interval, minus 20 to minus 30%. And it looks like, what, 2 in that next interval, 3 in the third one, and then it goes up from there. So that's a histogram, and it just describes this distribution, this population. When we go to cumulative relative frequency, we're going to add up the percentages, and you can see they do go up to 100%. So when we talk about the cumulative relative frequency, and sometimes we express this as f of x is the cumulative distribution number for our random variable x. So if we take a value here of 10%, then we would add up all the observations we had, and what percentage of the total is that. So we're at 60% of the observations are less than 10% here. So that's our cumulative relative frequency distribution. Here's a frequency polygon right here. It's just another way, so if you see something like this, you know what it is. What we've really done is just taken the midpoint for each of those intervals and plotted the frequency. And again, we're in numerical frequency here, not percent. Okay, some measures of central tendency. The first one and the simplest one, population mean. Add up every value and divide by n, the number of observations that you have. And we'll represent that population mean with the Greek letter mu. The sample mean, same idea. We use a lowercase n here to indicate we have a sample, and we've used the uppercase n to indicate that's how many in the whole population, all the possible outcomes. So with the sample mean, talking about taking the numbered ping pong balls out of the barrel, take 10 of them, n is 10, add them all up, that's what this summation sign means up here, of course, and divide by 10, and that's a sample statistic. That's our sample mean. Now the geometric mean is a little bit different, and that sample mean or regular mean, sometimes we'll call that the arithmetic mean. The geometric mean has to do with compounding, and we can solve for a compound growth rate. Now if returns are the same for a number of periods, if you have 5 periods and every period the returns are 10%, the arithmetic mean and the geometric mean are going to be exactly the same. But if there's variability in it, then the geometric mean is going to be less than the arithmetic mean, and it will be less by a greater amount when there is more variability of returns over time. So here's our formula. Here's our calculation at the bottom of the slide here. These R's are the returns for a number of different periods, n periods here we have. And so our compound return, say these are annual rates, and we've got n number of years. So we take those, multiply 1 plus those annual rates, multiply that all together, and then take it to the 1 over n power minus 1. Now, the important thing here, the calculation is fairly straightforward. The important thing, what are we solving for here? We're solving for the single annual rate of return that if we compound this for n years, we'll get the same results as we did with our annual returns. So if this is a stock index or a mutual fund, we have different returns each year, and we can figure out the equivalent annual compound rate. Let's look at a numerical example. Here we've got an investment account that had returns of 50% in year 1 and minus 50% in year 2. Calculate the average annual compound rate of return. Well, you might think that if you had an investment that went up 50% in one year and down 50% the next year, you'd be back to where you started. But that's not really the case. If you have $100 and that grows to $150, that's a plus 50% return. But what if it falls 50% the next year? Well, if it falls 50% the next year, it falls to 75, and we'll see that's a minus 50% return that second year. So the arithmetic mean is clearly 0. 50 minus 50 is 0, divided by 2 is 0. But here we want the average annual compound rate of return. Well, that can't be 0 because somehow we get from 100 down to 75. And take a look at our calculation here. Now we add 1 to that 50% return for the first year, multiply it times 1 plus the second year return, which is a minus 50%. And since we have 2 years return, we need to take the square root of that, and we get 0.866. Well, we need to subtract 1, and so we find out that the compound annual return has been minus 13.4%. And that makes sense because remember we started in our example with 100 and turned it into 75. So if you lose 13.4% of your money each year for 2 years, that's what will take you from that 100 to 75 over a 2-year period. And also note that order doesn't matter. That is, we could have in the first year our minus 0.5 and put our 1.5 over here, and it doesn't change anything. So no matter what order these annual returns come in, we're still just taking 1 plus those returns, multiplying them over the whole time period. So the order that they arrive in just doesn't matter at all. Okay, a weighted mean. Well, when we talked about the mean before, we divided by the number of observations. So we kind of gave each observation an equal weight. You can think of that as multiplying each one times 1 over n, and adding them up, that's the same thing as adding them up and dividing them all by n. Well, in a weighted mean, the weights aren't equal. Think about a portfolio, and we'll give you an example in just a second here, where you've got 60% of your money in stocks and 40% in bonds. Well, the portfolio return is going to be more influenced by the stocks than the bonds, so we can't just take the simple arithmetic mean. So here we're going to multiply each return times a weight, and those weights sum to 1. They're the percentage of the whole portfolio in the way we'll use this most of the time. Our last mean, we've had arithmetic and geometric. Now we've got the harmonic mean. Now the harmonic mean, as far as I know, the only use we have for it is to calculate the average cost per share when you're making equal dollar purchases each period. You may have heard of some of this as dollar cost averaging. Somebody buys shares in a mutual fund, you invest $500 a month. Well, when the price is low, you get more shares. When the price is high, you get less shares. And so we can figure out the average. Now here's the formula for the harmonic mean. We've got n here. That's the number of periodic purchases. Here is the price at each period, I through n, however many periods we've got. So in the denominator is the sum of 1 over those prices. So let's do an example, and I think I can show you a way where you can remember that formula quite easily. An investor buys $3,000 of a stock at the end of month 1 at $20 a share and $3,000 at the end of month 2 at $25. So it's a simple example, but we can apply this. So the question becomes, what is the average cost per share of stock? Well, that question is the same as what's the harmonic mean of 20 and 25. So we would set this up. Look what's in the numerator here. That's how much we invested, $3,000 a month for 2 months. What's in the denominator? Well, this is the number of shares we got the first month. We got 150 shares. Price was 20. We spent 3,000. The next month, the price was up to 25, so we got less shares. What's that? I think that's 120 instead of 150. So if you look at that, you can see we have calculated the average price per share. In the numerator, we've got the $6,000 we invested. In the denominator, we've got the total number of shares we acquired. So we have figured it out, but look at what happens. We can take that 3,000 out. It doesn't matter. It's in the denominator in both pieces, and it's in the numerator, so we can just cut that out, and that gets us to right here. Well, there's your formula right here. 2 is n. Okay? 1 over 20, that's 1 over x1. And 1 over 25 is 1 over x2. We summed them up, and so that's where that formula comes from. And we end up with an average cost per share of $22.22 per share. Well, what's the simple average? The simple average is $22.50. So one of the things about the harmonic mean is it's less. We'll see it's also less than the geometric mean, but it's definitely less than the simple average of $20 and $25 per share. So let's just do this calculation, simple calculation, 3 numbers. What's the arithmetic mean of 2, 3, and 4? Well, that's 3. Add them all up and divide by 3. 9 divided by 3? Yep, that works. It's 3. What about the geometric mean? We said that was going to be less. Let's see if it is. If we multiplied all 3 together and took the cube root here, we'd come up with 2.88, so that was less. And finally, the harmonic mean. 3 is n here. We've got 3 different prices, so we've got 1 over each of those all added together in the denominator, and we get 277. So this is just to help you remember and to drive this point home that as long as there's variation in the values, the arithmetic mean is the largest, the geometric mean is slightly less than that, or I should just say less than that. I'm not sure, it has to be slightly if there's a lot of variation. So the geometric mean is less than that, and the harmonic mean is less still than the geometric mean. Let's look at a portfolio return example and use our idea of a weighted mean, I think, here. Consider the following portfolio. At the beginning of the year, we've got $4 million in cash, $6 million in bond, and $10 million in equities. So we've got 50% of this account in equities, we've got 30% in bonds, and 20% in cash. So now, if the returns are 5% on cash, weren't those the days? 7% on bonds, that was pretty exciting too, and 12% on equities, what was the portfolio return? Well, here we're going to use a weighted average, and the weights are just going to be the percentage of the total portfolio that are in each of these asset classes. So 5% in cash, 5% return, the weight is 4/20ths or 1/5 of the portfolio, so we take 1/5 times 5% and we get our 1%. We've got 6/20ths, 30% of our portfolio in bonds, so the weight is 0.3. 7% times 0.3 is 2.1%. And stocks, well, our return was 12% and our weight is half of the portfolio. So 0.5 times 12%, we get 6% here. Add them all up, and there we've used the weighted mean to calculate the returns on the portfolio. And we could also do this for expected returns. If these weren't the actual returns for the year, but we were looking forward and saying, well, these are the expected returns on cash, stocks, and bonds, then this would be the expected portfolio return. So no difference there. We'd use it exactly the same way. Our next concept after our means, remember, what are we? Well, we're looking at measures of central tendency, right? Well, another one is the median. And the median is just a number that's in the middle of the data set. Puts half of the observations above and half of the observations below. That's the median. Now, if we have an odd number of observations, that's pretty easy. Just lay them out in numerical order, pick the middle one, you've got half higher, half lower, and the median is 7. If we have an even number of observations, then it's the average of the two middle ones. So here we've got 4 observations, 3, 9, 10, and 20. Well, we want to be halfway between those, so let's just go halfway from 9 to 10 and say our median is 9.5. So why do we even care about the median? Well, the median is a measure of central tendency, and it's not as affected by extreme values as the mean is. You may have heard when they talk about real estate, they always talk about, well, what happened to the median price in this market? They don't use the mean price. And I can show you why. Let's illustrate this idea that the mean is more affected by extreme values than the median. Let's use the bottom 4 here. We've got those 4, and we could figure out the mean of that, right? 3 plus 9 is 12, and 30, 40, 42 divided by 4. So the mean is, whatever it is, 10.5, something like that. Now, what would happen to that mean if this third value, instead of 20, was 20 million? Well, our mean is pretty well affected by that. We're going to be somewhere over, just barely over 5 million is our new mean, with that observation changing from 20 to 20 million. But what happened to the median? Well, our midpoint is still the same. We're still halfway from 9 to 10. So we increased that top value, that top observation or outcome, from 20 to 20 million. The mean changed a lot. The median didn't change at all. So that's why we say the median's less affected by extreme values, and that's why I think they use it for house prices and looking over time at what's happened to them. the sale of a very large, expensive house in a neighborhood, a geographic area, could make the mean bounce all over from month to month. The median, not so much. So that's why they use it. The mode, just the most frequently occurring outcome. So in our example here, we put all our outcomes in numerical order, and we saw we had 3 8s here. That's the mode. Now data sets can have, they only have one mean. They only have one median. But they can have more than one mode. If there were another 5 in here, if I could just squeeze one in here like this, then we would have 2 modes. There are 2 values that occur the same number of times, the greatest number of times, 5 and 8. And in that case, we'd say we had a bimodal distribution. So we can have more modes. Don't necessarily have to, but we can. And only one median and one mean. Now, we talk about quantiles or quartiles, which are 25%, decile, that's 10% increments. And 50% of the data points are less than the 50th percentile. Well, the 50th percentile sounds just like the median, right? So let's look at some data with 17 observations and calculate a percentile. We're going to calculate the 70th percentile. And the way we do this is we take the number of observations, 17, and we add 1. And then we multiply times 0.7. Now, this 12.6 is not the value for the 70th percentile. It's the position among our 17 observations. So what we really have here is 12.6 means we're 6/10 of the way from the 12th observation to the 13th, when we put them in numerical order. So that's the 6/10 part. So remember, it's 1 plus n, 1 plus the number of observations, times the percentile you're looking for as a percent, 0.7, and that gives you the location of the 70th percentile. Our next 2 concepts here, as we introduce some more words and terms, are the range and the mean absolute deviation. The range, pretty straightforward. How far is it from the highest to the lowest numerical value? So for those 4 returns we have there, the range is the difference between the largest, 22%, and the smallest, -5%. That distance between them, 27%. So now we're not talking about measures of central tendency, we're talking about measures of dispersion. How spread out, how dispersed are the observations? And in some sense, how volatile is the random value? The mean absolute deviation is the average distance from the mean. We use the absolute values, and we add them all up and divide by 4. Now, the thing is, with these absolute values, that's why I talk about it as distance, measure it as positive distance. If we took how far each, if we took the mean minus, each observation minus the mean, we'd get some negative values, some positive values. And in fact, by the way the mean is calculated, if we added them all up, we'd get 0. The average difference is 0. But with mean absolute deviation, remember, we want the absolute values. So here we've got 15 is 4 away from 11, and -5 is 6 away from -11. 12 is 1 away from 11, and 22 is 11 away from 11. So we take all those absolute values, add them up, and divide by 4. That's the mean part. The absolute value part is the absolute part, and the deviation part is how far is each one from the mean of the distribution. So that's our mean absolute deviation. It's a measure of how spread out these things are, these observations are around the mean. We aren't going to use it for anything I can think of in the level 1 curriculum, except asking questions about the mean absolute deviation. Okay, the measure of dispersion that we'll use mostly, and that's most widely used in finance, is the variance or the standard deviation. So this is a measure of how spread out they are, and how we calculate this. We take the average of the squared deviations from the mean. So here, remember, our population mean is mu. These xi are all our observations. So in parentheses there, we have how far is each observation from the mean. We square that, we add them all up, and then we divide by n the number of possible outcomes in the population. And so that's the population variance. We refer to that with the Greek letter sigma, but we square it, sigma squared. And if we take the square root of that, we get just sigma, and that's what we use for the standard deviation. Standard deviation is the square root of variance. Variance is always positive because all those numbers in the numerator are squared, so they're all positive values. So standard deviation also is always squared. So that's for the population. Now, usually we have a sample, and when there's a sample, we use S for the S squared for the variance and S for the standard deviation. But now we divide by n minus 1. And there's some great mathematical reasons for that. It makes this an unbiased estimator of the true variance and all that. But I think for our purposes, all you have to remember is to use n minus 1 when we have a sample, and use n if we have a population. If you're told you have all the possible outcomes, then use n. Let's do a numerical example here. We've got 4 stock returns. It's a small sample size. It's not going to make a lot of sense, but we can certainly illustrate this. What are the population and sample standard deviation? Well, if that were the whole population, if those were the only outcomes, we take the deviations from the mean. We know that mean is 11%. So we take all those differences, subtract the mean from each one, square those, add them all up, and then divide by 4. That's n. We've got 4 observations, and we get 98.5. And if we take the square root of that, we get 9.9%. Now, we're working in percentages. And in that case, this 98.5, well, the units of variance are, in this case, percent squared. So really the units are 0.0001. So if we said 98.5, we mean 98.5 times 0.0001, because that's the units we're in. And so that would really be 0.00985. And then if we take the square root of that, we get 0.099, and that is 9.9%. So standard deviation is always in the units that we start with, that we're measuring our variable in. So standard deviation comes out in percent here. And also, if we took this decimal, if we took the square root of that, we'd also get the 0.099, but we can take the square root of 98.5, get 9.9, and know that we're back to percent. If we were measuring rainfall in inches, then standard deviation would be in inches. If we were measuring rainfall in centimeters, standard deviation would be in centimeters. And so as you'll see, as we get into sampling and confidence intervals and hypothesis testing, having that standard deviation in the same units as what it is we're measuring is really helpful. The only other thing on this slide to note is that we'll divide by n minus 1 if we had a sample, which is most likely the circumstance here, that we've got returns on 4 different stocks. So we divide by n minus 1, 3 in this case. We get 131.3, of course a little higher value, and then also a higher value for the sample standard deviation, which is 11.5, the square root of 131.3. Chebyshev's inequality. Well, Chebyshev's inequality says for any distribution, here's a formula that will tell you the minimum percentage of observations within that many standard deviations of the mean. So we've got a distribution, it's spread out like this, it's got a certain standard deviation. But we haven't said it's a normal distribution or it's an F distribution, or we haven't said anything about the distribution. So that's the important thing about Chebyshev's inequality, is that it applies to any distribution. And it just says this minimum percentage is 1 minus 1 over k squared, where k is the number of standard deviations we're talking about. Now, it doesn't make any sense when k equals 1. Well, when k equals 1, it comes out to 0. And saying the minimum is 0, it's not very illuminating. So let's do it for 2 standard deviations here. The minimum percentage within 2 standard deviations, either side of the mean, is 1 minus 1 over 2 squared, 1 minus a quarter, 75%. So it says, well, here's the mean. It's spread out, has this standard deviation, this measure of dispersion. Well, at least 75% of the observations for any distribution are going to be within 2 standard deviations either side of the mean. That's kind of a standalone learning outcome statement. Doesn't really lead to anything. It's just something that's fair game for the exam that you need to know. Okay, a couple more measures we need to look at here. Coefficient of variation. We may have a situation where we have 2 assets. This asset has a higher expected return, 5% on average, than this asset, which has a lower expected return of 5% than asset B. But asset B has a higher standard deviation. Asset B has more risk, which is how we use standard deviation in finance, a measure of the uncertainty about the outcomes or the risk of holding a certain security or portfolio. So asset B has higher standard deviation and higher return. But we think investors dislike risk, standard deviation, and like higher expected mean return. So how do we do this trade-off? How do we figure out which of these is more attractive? Well, one way we could do that is to use this measure, coefficient of variation, which is the standard deviation over the mean. Now, so you don't get this upside down, at least one way to remember this is when you think coefficient of variation, I want you to think, hey, that's a measure of variation. So let's put variation in the numerator. It's actually variation per unit of expected return or average return. So let's compare these 2 now, and we see that asset A has a coefficient of variation of 2, asset B has a coefficient of variation of 1.5. Which one do we like better? Well, we like the lower coefficient of variation because remember, it is a measure of risk or uncertainty, and we prefer less risk and less uncertainty, other things equal. So lower coefficient of variation is better, less risk per unit of return. So you took on less risk for each 1% return that you earned, and that's a better asset or portfolio. Here we've got the Sharpe ratio, named for Nobel laureate professor William Sharpe. The mean portfolio return is 17%, the standard deviation is 9, and the average risk-free rate is 5. What we do in the Sharpe ratio is we take the return on the portfolio, or the average over some time periods, subtract off the risk-free rate for the period, or the average risk-free rate over those time periods, and divide by the standard deviation of returns. So now, instead of a measure of variation per unit of return, we've got a measure of unit of return per variation. And the reason we subtract off that risk-free rate, if we have a risk-free investment, it is certain. and it has a standard deviation of 0. So, in finance theory, we explain that if you want a higher return than the risk-free rate, you're going to have to take some risk. Here, we've taken the difference between the return you would have earned taking no risk, that's the risk-free rate, RF, and the return actually earned, and divide that by the units of risk that you took on in order to get those returns. So our calculation here, 17 minus 5 over 9 gives us 1.33. That's our Sharpe ratio. And a higher Sharpe ratio is better. If you get more extra returns per unit of risk than a competing manager, then you've beat them. Okay? You did better in that market period. Given the risk that you took on, you earned more per unit of risk. So that's the Sharpe ratio. Well, we've talked about all sorts of measures of central tendency. We've talked about measures of dispersion. And so now we want to talk about a measure of symmetry, skewness. That's a normal distribution, or pretty darn close to it, our bell-shaped curve, or bell curve, as we often call it. And the normal distribution is symmetric around its mean. So when it's symmetric, its skew or skewness is 0. And for the normal distribution, the mean, the median, and the mode are all equal at that central point. The mean's the same as the median because of the symmetry, and the mode is because the highest probability. Maybe I should mention when we draw this, this is kind of probability on this axis here, and then these are the values along the horizontal axis. So that means probabilities are higher of outcomes in here than they are over here or out here. But the height of this curve shows at least the relative probabilities of getting different outcomes along the full range of outcomes. So here we've measured skew equals 0, mean equals median equals mode. Next up, let's pull on this thing. Let's pull on that right-hand tail and give it some skewness, right? More outliers, more extreme values out here. We've pulled that out. Well, this is called positive skew, or positive, or right-hand skew, clearly, because it's on the right. Now, what happens with that? Well, when there's positive skew, now the mean is greater than the median is greater than the mode. Remember, we said extreme values affect the mean more than the median. So that explains why the mean has moved the most here. The median, well, it's in the middle, so that's easy to remember. The mean moves most, the mode doesn't move, the median's in the middle. Now, for left-hand skew, we get just the opposite result. The median's still in the middle, the mean moves the most, and the mode stayed unchanged. So if we have negative skew, where we've got some extreme values in the negative or left-hand tail here, then the mean is less than the median, is less than the mode. Okay? And that's what this learning outcome statement wants you to know. First, it wants you to know what left and right skew are, and then what are the relative positions of the mean, median, and mode based on the skewness of the distribution. So, we've had the mean, we've had the variance, we've had the skewness. This is our so-called fourth moment of a distribution, and kurtosis is a shape parameter. And how are we going to measure shape with a single number? Well, we're going to measure it relative to the shape of a normal distribution. A normal distribution has skewness of 0, it's got some mean, it's got some variance, but given those parameters, it's got a specific shape. When we talk about kurtosis then, we're going to talk about excess kurtosis, because the kurtosis of a normal distribution is 3. Now here we've shown a leptokurtic distribution, it is more peaked. It's higher in the center there, and the tails are fatter. And that's what we're concerned about, is fat tails. Sorry, found that humorous. We're concerned about fat tails. And remember, I said the height of this thing, this distribution, is the probability. So when we talk about fat tails, we are talking about higher probabilities, probabilistic statements based on assuming that a distribution is normal if, in fact, that distribution has kurtosis greater than 3, that is, it has positive excess kurtosis. Always care about whether the distribution of whatever we're interested in is approximately normal or maybe non-normal. Maybe it's leptokurtic, there's fat tails, and we're underestimating the probabilities of either extremely good or extremely bad outcome. Well, extremely poor outcomes usually we're most concerned about. So that's why we care about kurtosis. If kurtosis is less than three, then we say that excess kurtosis is negative. And instead of being leptokurtic, it's going to be platykurtic. I think it's from Greek for flat or something like that. But anyway, instead of being more peaked, it's less peaked instead of having fat tails, it has normal tails. But that doesn't scare us. We're worried about high probabilities of extreme outcomes. And so we're concerned about positive excess kurtosis. We're concerned that our distribution of outcomes may be leptokurtic. So I think this just sums up what's already been said. Oh, except for the last point, we're okay down to here. For that last point, if excess kurtosis is greater than 1, so we're saying a kurtosis of 4 or 2 or less or 4 or more, then that's a significant deviation from normality. That's the point of that last phrase there. Okay, let's do a little example here. Consider investment returns over 5 years of 10, 15, minus 4, 9, and 5%. The arithmetic mean of those is 7%. And we can interpret that as the best estimate of a single year's returns. If we had those 5 years of returns, we say, hey, the distribution, the underlying process has not changed. What's your best guess of next year's return? That's going to be 7%. That's going to be the arithmetic mean. But what if we said, well, what's your best guess of the compound return over the next 3 years? That's not 7%. That's going to be the geometric mean. We've got some variability here. The geometric mean is less than the arithmetic mean. But if we've got a multi-year holding period, and we're talking about a compound rate of return, we need to use the geometric mean. If we're just looking simply at single observations, 1 year, then the arithmetic mean is statistically our best estimate of next year's returns. Now notice our best estimate is 7, and 7 hasn't happened. But what we're saying is that if our estimate is 7, our expected miss from 7 is minimized. That's what we mean by our best estimate of a single year's returns. We'll see you in the next segment.